Okay, so new topic, kind of new topic today. So this is in the same section as the chain rule. We kind of finished talking about the chain rule part of the chain rule section. This could be its own separate section. I guess the authors decided that it was a little too short to be its own section, but adding it to the chain rule section makes the chain rule section really long. So, what are you going to do? Yes?
For the midterm, are we going to be tested on all the material?
It's up through and including what we finished today, and I'll send out an email with the exact details today, unless I forget, at which point you're all requested to send me a reminder, in which case I'll do so, yeah. So to be determined. Yeah. Okay, so implicit function theorem is a nice application of the chain rule. It addresses the following question. Suppose you're looking at a level set of some function. Now we're going to start off with this function of two variables case. Some of y'all might have seen a version of this in high school. I'm going to complain about the version of it that you've seen in high school. No surprise there. Okay, but there was a multivariable version. We're going to get to that too. Okay, so here we go. Here's the question. You're looking at a level set of a function of two variables. Is it possible to view this, what I'm going to call locally, and I'll expand on that in a second, as the graph of a function of one variable? Now let me point out what we're doing here. Don't forget to notice. Here on the one hand, we're looking at a level set. You know what? Let me do this with a pencil. We're looking at a level set of this f function, right? And we're asking, could I view it as a graph of this other function? Now let me point out what we're not doing. We are not looking at the graph of this function capital F. Don't care. This is not what we're worried about. So the graph of this function capital F would be a surface in 3 dimensions. Got nothing to do with what we're doing here. Everybody clear on that? Also, we're not asking what are the level sets, right? What are the level sets of this other function y? We're not interested in that either. Right? So now, granted, it is true if you have a single function, then you can consider what does its graph look like? What do its level sets look like? That gives you two different points of view, two different geometric points of view on one function. Again, over here, you could talk about two different geometric points of view on that one function. We're doing kind of the opposite. We're asking, given a single geometric picture, can I view it as in different ways relating to two different functions? Everybody see the difference? Right? So don't be distracted. We're not looking at the graph of capital F, and we are not looking at the level set or level sets of that function that y that we're speculating about. Okay, so yeah, let me get rid of all this junk here. Okay, so now you might recall we've already kind of addressed this question partly. Remember when we were talking about level sets and graphs, I made the observation that every graph is a level set. Easy examples, though, to show that not every level set is a graph. Fails a vertical line test. Easy examples. Circle, for example. Right? Okay. All right. So we are asking here a slightly different question, though. Can I locally view it as a graph? Locally means near a particular point on the curve. Right? So we're going to forget about all the rest of the curve. So we're going to throw away. I don't care about all these other points on the curve. Forget about all that. Can I locally view this level set as being a graph? And notice this, at that particular point on this particular curve, this one little piece of that curve near that point passes the vertical line test. And yes, at that point. Yeah? On the other hand, look at this point, this other point there. Get rid of this stuff's in my way. Look at that little point. Now again, forgetting about all these other points over here. Don't care about all of this. Unconcerned about all of that. Who cares? Right? Just looking at that little piece of curve. Can I view this as being a graph of something? And the answer is no. right? This particular point right there that I've chosen very strategically, no matter how much of the rest of this curve I throw away, it's always going to fail the vertical line test. So the answer to this question is sometimes no. Even with this locally little caveat. Everybody see what's going on there? Okay. All right. Obviously in high schools they don't talk about this very much, if at all. So let's try to ask the question, well, how do I distinguish between these cases? Right? And some of you might be saying, oh, well, look at this function and ask whether the derivative is finite or, doesn't exist, infinity, however you want to say it. Right? If you have a finite derivative of that function, then it's cool. Right? And if your derivative is either infinite or doesn't exist, then something's wrong here. The answer is probably no. Okay. So let me tell you what's fundamentally backwards about that. In speculating about whether or not a certain function exists, you cannot cite the derivative of this thing that you have yet to establish even exists. Everybody see the problem there? It's fundamentally backwards. So what we need to do is we would like to figure out a test. We would like to arbitrate this question without making any reference to that function. The function whose graph gives me my piece of the curve, whose derivative would sort of seemingly interface with this question so conveniently, we're not allowed to make reference for it. We don't even know it exists yet. So what we want to do is arbitrate this question by looking only at the function whose level set we know we're looking at. All right, so here's how that breaks down. It goes like this. Here's what a no would look like. Right? There's just, appeal to the intuition of what came above. By the way, what I'm doing here is not rigorous. It's not intended to be this is not Math 431. This is Math 212. Right? If you take Math 431, you'll see a much more robust discussion, and we're not going to do that. But I appeal to your geometric intuition. This is what a no looks like. Right? The curve wraps under itself. It's the fact of it wrapping under itself that makes it fail the vertical line test. Specifically, it has to be in the moment of wrapping it under itself at exactly that point. Well, that means it's going to have a vertical tangent line. Now, notice I did not say derivative is equal to infinity. Right? If there were a function y, then you might argue that the derivative of y doesn't exist, or the derivative of a y, maybe equals infinity. But f is not y. F and y are different functions. Really different functions. Okay. But here's what you can say in reference to f. If there's a vertical tangent line, that means that as you are moving along this curve, which let's see if I'm artistically competent to trace that curve. As you are moving along that curve, don't forget this curve is where f is a constant. And I wrote 0, but it doesn't make it be any constant. If f is constant, then as you are moving along that curve, f is not changing. That's what constant means. Yeah? Right? So f is not changing as you move along that curve. Oh, hey, also, notice as you're moving along that curve at the point in question, you are moving vertically because we have a vertical tangent line. So as we are moving along that curve, as we are moving in exactly the vertical direction, the function is not changing. And here's an easy way to write that down. Combining these two ideas, f is not changing as you move in the y direction. Tells you the partial of f with respect to y is equal to 0. Does that appeal? Everybody happy with that? Okay, so there's some geometric ideas here to kind of digest. Give yourself some time. Re-listen to this portion of the lecture recording if you need to digest that idea a little bit more. But fundamentally, if you've got a problem, you've got a wrapping under or wrapping over, depending which way you're going. That implies a vertical tangent line, and that implies that partial derivative is equal to 0. Notice that we are making a reference to this function. We are making no reference to y as a function of x. Right? We are in reference to this function, notice that we have two independent variables, x and y. Y is an independent, it's an input variable. So we're talking about y as not an output value. We're talking about y as an input value, and thus we can talk about that partial derivative with respect to y. Okay, yeah?
Can you explain the connection between f of x, y, and y of x?
Yeah, so this is this business about, two different functions that relate to the same curve, but in different ways, right? So this curve is the graph of this function f, but it's a level set of this function f. So they're two different functions, totally different functions. I mean, there's algebra that relates them. I guess you could take the first equation, solve for y as a function of there's connections, right? But they are different functions in that way. Okay. All right. So here's our answer, right? Again, we're not presuming the existence of a function that we're trying to decide about the existence about, right? We're not making that immediately circular error that we talked about. We have a test. If there is a problem, let me write this down. What we've shown here, bad color choice. What we have shown here is that if there is a problem, then that implies the partial of f with respect to y is equal to 0. And then the next step, this statement here, is what we call the contrapositive. Do y'all remember the contrapositive from ancient history way back when in high school? If P implies Q, then not Q implies not P. Anybody remember that one? If you don't remember the contrapositive, here's the way to think about it. If P implies Q, and then if not Q happens, well, wait a second. If not Q happens, P couldn't possibly be true. Look at that. If P is true, then Q is true, but we already know Q is not true. So if you know not Q, then you definitely know that P is not possible. Therefore, you know not P. Right? So that's kind of the rationale behind the contrapositive construction. And so anyway, it's in the form of the contrapositive that we actually get what I'm going to call a convenient test. And the test goes like this. Whatever this function is, whose level set is the curve in question, if you take the partial of that with respect to y and you get not 0, you're good. Yeah.
If you were to take the inverse of that function.
What function?
Of I guess a function. And to use this test on the vertical line test.
So wait, you're talking about you want to take the inverse of this function here?
Yeah.
That we don't know exists yet?
I guess if you were to run this test on a function, right?
Oh, so the test that we have is a test on this function.
Okay. If you were to get the inverse of that.
I don't know what that means. We have a function from R2 to R1. It's got 2 input variables and 1 output variable. It's not an invertible function. Yeah. No, and I mean, it's a reasonable line of inquiry, right? But it's something that dead ends immediately, unfortunately. Does that make sense?
Yeah.
Okay. It's a good thought. Yeah. Okay, so this is our test. The function whose level set you're looking at, take its partial with respect to y. If you get not 0, anything other than 0, positive, negative, big, small, who cares? Anything other than 0, you're good. Y exists. Yes?
Yeah, so the you're good means you have a local function y of x at that.
Then you can, locally, that means you're looking at this situation here, that even though your curve is described currently as a level set, you can view that. It could be argued that there exists this function y. Now, how you find the function y, that's an algebra problem, right? What we conclude here is that at least it exists, right? We are not on a wild goose chase trying to find some function that doesn't even exist in the first place. Yeah. Okay. All right. There's a multivariable version of this. This is the multivariable version. Oh, by the way, let me say, y'all might have seen something kind of vaguely akin to this in a high school class, but they usually kind of skip over the, hey, how do we know this function exists business, right? And they just assert, hey, suppose it's given in this way. Let's compute y prime. right? And they call this implicit differentiation. They just go right to, at least, I don't know, let me not assume about your high school. In my high school calculus class, it just went straight to, what is the derivative of y? No discussion of whether it exists. And that's incomplete. Okay. All right, so here's the multivariable version. Suppose we are looking at a level set of a function of 3 variables. Okay, now we're looking at a surface in space. Can I view this surface as locally being a graph? Right? I know it's a level set. Can I reinterpret it as a graph? Said differently, near a given point, and just to start off, let's say maybe, near that point, locally, if I say I just want to look nearby on this part of the piece of surface, can I view that z as a function of x and y? Well, sometimes yes, right? Here, yes, the vertical line test locally passes, right? No problem. I'm not worried about stuff that happens down there. We're only interested in locally, right? So sometimes yes, and sometimes, such as at this point, no. Look what happens if I, looking locally, that's harder to draw than it looks, so forgive me. But the surface is in the process of wrapping under itself, and no matter how little of this surface you look at, right, you're going to be double hitting that little piece of surface, right? You're going to fail the vertical line test. There and there. So sometimes yes, sometimes no. How do you know when it's going to happen? Well, it's a very, very similar argument. If there is a problem, such as that, the surface is wrapping under itself. You can see that happening in this picture. If the surface is wrapping under itself, that means it has a vertical tangent plane, by which I mean parallel to the z-axis. Right? If it has a vertical tangent plane, I appeal to your intuition, then as you are moving in this surface at this point in such a way that at that moment you're going straight up, because I'm parallel to the z-axis, I know there's a tangent vector that's exactly parallel to the z-axis, right? As you're moving along that curve, the function's not changing. You're on a level set. Level set means not changing. That means that as you're moving in the z direction, this partial of f with respect to z is 0. Right, so again, that's what we can see from the picture, and the contrapositive gives us what we want. If the partial of f with respect to z is not 0, no problem. Okay, so here's the theorem stated in full. Now you'll notice we started off with a function of 2 variables. I've drawn the picture here and made the case again for a function of 3 variables. I'm going to state the theorem here in kind of more general terms as a function of n variables. Don't try to visualize the picture. Your brain will blow up, right? You couldn't possibly visualize the picture, right? But the theorem continues to hold for what I'm going to call morally the same reasons, right? Again, this is not a 431 class. This is 212. If you want to view one of the input variables as a function of the others, right? So if I want to view this variable, xi, as a function of all of the other variables, I address that by taking the partial derivative of f with respect to that variable, whichever one you want to view as a function. Take the partial with respect to that variable, confirm that it's not 0, then that function, that variable can be viewed as a function of the others. Okay, notice the pattern, right? If I want to view y as a function, take the partial of f with respect to y. If I want to view z as a function, take the partial with respect to z. Okay. All right. Okay. So that arbitrates the question of, does this function even exist? Now, how do you find the derivatives? I'm going to skip through my own notes to kind of the bottom of the next page. Let's look at this picture here. I like to have a little diagram to think through the argument. It's a tricky little calculation. Here's our initial thing. We've got f as a function of x1 through xn. We've got a bunch of input variables. We're looking at a level set of that function. Right? And suppose we've already done the check. We already know the partial of f with respect to xi is not 0. So I know that I can view xi as a function of the other variables. Let me append this diagram appropriately. Xi is a function of these other variables like this. Note the conspicuous absence of xi down here. Xi is a function of the other variables. I'm not making the much more modest suggestion that xi is a function of itself. That's not what we're interested in. Right? Okay. All right, so nothing in that spot. That's empty. Okay, so the way we're going to get at the thing that we're interested in, keep in mind, I'm interested now in computing a certain partial derivative. I want to know, this thing that I have now decided is a function. Xi is a function of the other variables. How would I, for example, take its partial with respect to xj? I don't know, one of the other input variables. Right, partial of xi with respect to xj. Okay, well, come down here to our picture. Here's our xi. And here's our xj. And this partial derivative here is what I want to compute. Now, everybody on board? Okay, well, let's think through some details. When you take a partial derivative, don't forget what partial derivative means. Partial derivative means that all the other input variables you hold constant. So in asking for the partial of xi with respect to xj, that means x1 is to be thought of as a constant. x2 is a constant. Blah, 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 blah. All of these input variables are constant. Not xi, of course. Xi is a function. Right? Not xj, of course. I'm taking the partial with respect to xj. But all these other variables are held constant. Well, okay, now, obviously, that means that up here, all of those variables are held constant. Everybody on board? This purple partial derivative that we're trying to compute means all this other stuff is constant. Okay. All right. The foot in the door to finding that purple partial derivative is to, this is another mathematical bank shot. I'm a big believer, right? It's a common strategy in math is if you're trying to compute something, compute a related quantity that you know two different ways. And then capitalize on the fact that you know what these two things are, and then sometimes stuff just works out. So that's what's going to happen here. I'm going to compute now I'm going to compute the partial of f with respect to xj, by which I mean, I shouldn't have used blue there. Green, purple, orange. How about orange? Partial of f with respect to xj, by which I mean I want to compute the partial of that with respect to that. Now here's the two calculations I'm going to do. The first one's an easy one. I'm attempting to compute the partial of something that I know is constant. Right? Everybody see the first calculation? It's constant. What's the derivative of a constant? 0. Okay, so on the one hand, I know it's 0. On the other hand, I can use the chain rule. This is why we're in the section on chain rule and doing this calculation. This is as it turns out, we see here, a perfect application of the chain rule. This partial derivative, partial of f with respect to xj, I'm going to write down, there's various different paths that I've got to think about. How can xj cause changes in f, and how do those add up? And by the way, add up to 0. Let's not forget that, right? But there's a bunch of different paths. There's the first one. And I don't have to write that down because x1 is constant. So, right? It can't change. There is no propagation of changes through x1. x1 can't change at all. Everybody happy? Okay, so most of the terms just go away. There's really only two terms that I have to write down. There's that one by way of xi, and there's this one by way of xj. So let's write that down then as, let's see here. I'm going to have partial of f with respect to xi times partial of xi. Oh, I've got this written down already. Sorry. Zoom out one notch. There it is. Let's do this. The first term, let me color code better, right? And then the second term, again with the colors. Second term is that. What's the partial of xj with respect to xj? Well, of course, that's 1. Everybody on board? Yep.
Why are xi and xj not constant then?
Yeah, because in this question, right, I've decided that I want to compute the partial of xi with respect to xj. Let me go back to this picture that I wrote down. Okay, well, anyway, one of the first pictures I wrote down here was that I'm interested in computing, viewing xi as a function of the other variables, and from that point of view, I want to view the partial of xi with respect to xj, and that means I look at xi as input variables. Other than xj, I hold all the other input variables constant, and then I take the resulting single variable derivative. Right? Yep.
How can you have that like yellow term if df is just equal to 0?
Because it's the total that's equal to 0. Right? So let's see. Let me do this in the orange. The total partial of f with respect to xj, considering all different paths, is 0. But not one path at a time. I'm not saying all the individual terms are 0. I'm saying grand total f isn't changing. But the way that f fails to change is just that the sum of all of the contributions to the change in f has to equal to 0. Yeah. Yep.
But isn't like the partial of f with respect to xj looking at one path rather than all the paths?
So this is an awkwardness in the notation, and this is something that you definitely have to worry about. Don't conflate. I mean, you just, I don't know of any notation that bypasses this problem. We don't want to conflate the partial of f with respect to xj there, which is, I think, what you're asking, right? Versus the partial of f with respect to xj kind of here, right? There are these two different xj's, and what I'm computing here, when I say is equal to 0, is the partial of f with respect to the first xj. That xi is a function of. Don't forget, we've got to keep that in mind. Xi is a function of xj. That means this one. Does that make sense?
Why would that be 0?
Because f is a constant. And constants don't change. Therefore, derivatives of constants are always 0. Yep. Does that make sense? So, by the way, let me just point out, there's a lot of little confusing details involved here, right? And so, you're definitely going to have to, this is a situation where I think the fact that we're video recording this is so valuable. You can go through and listen to each little step. Again, whichever is the one little step that you're momentarily stuck on, go and listen to that discussion again, and it hopefully should clarify. Okay. Time is a factor, though. I'm sorry. I know there's always questions, but we've got to get some more material. We're falling behind again. And I've already. This is one of my favorite topics to talk about, and I tend to go on and on more than I probably should on this. Okay, so anyway, by way of these arguments, then looking at this path that gives that term, and this path that gives that term, and keeping in mind that because f is a constant, we know that in total you get 0. don't forget the partial derivative that I'm looking for. Right, partial of xi with respect to xj, that's that guy right there. Solve for it, and there you go. Now, let me take a quick moment to recognize this looks wrong. Right, I get that. Everyone that looks at this the first time and thinks, okay, well, obviously you've made a sign error because, well, you know, right? Those cancel. Don't those cancel? Seems like those ought to cancel. And what's with the minus sign? The minus sign seems just, dare I say, obviously wrong. What's going on there? Well, what's going on there is that, you know, this is one of the unfortunate things about this notation. We write partial derivatives as fractions. And, I mean, from a certain point of view, with a certain set of assumptions, they're kind of fractions, but they're really not fractions in a larger... You cannot just treat them as fractions willy-nilly, right? So when we write partial of f with respect to xj, this thing right here is making a huge assumption that is not true elsewhere in this expression. That says that we're viewing xj as the only input variable that's not constant, and that all of the other input variables are constant. But not throughout the rest of this problem. Check it out. xi is not a constant throughout the rest of this question. Right? So in this partial derivative, when you compute that partial derivative, you're assuming xi is constant. When you compute this partial derivative, right, you're assuming xi is not a constant. So these are simply not the same thing. You can't cancel them because they're different things. I mean, really, no kidding, fundamentally different things. Does everybody see what I'm talking about there? So now it invariably happens. I'm going to always make a big deal out of this in the lecture, and yet it remains that it happens every time. Oh, I didn't want to erase all that. Sorry, I forgot that. Okay, fine. It happens every term that students will write down. Students will write down this and proceed and do the calculation because these are derivatives that are easy to write down and get an answer. And it is so fundamentally wrong, right? I mean, in other words, this is what you would assume is true if you have absolutely no understanding of how to do implicit differentiation, right? So, I mean, accordingly, this is worth 0 points. It's going to happen. Somebody's going to do this. That's going to be worth 0 points. Don't say I didn't warn you. Okay. Because it is, again, it betrays a fundamental misunderstanding of what's going on. It betrays thinking that these partial derivatives are fractions of well-defined, things that are uniquely associated to the individual little differentials, which they aren't. And it's naive and wrong. Let's say it differently. Nothing about a solution that is done that way is valid. And so I can't give partial credit if nothing on the page is correct. Right? Everybody see what I'm talking about? So don't make that mistake. Don't forget this minus sign. Anyway, okay, enough of that. Okay, so here's an example. Suppose we're looking at this surface. Now, this is a surface, right? Let me admit, I have not the slightest idea what this surface looks like. Yikes, right? There's a cubic for crying out loud. It doesn't have any rotational symmetries. Oh, gosh. I mean, I guess if I really had to, I could probably figure out. But, man, it's not clear what this surface looks like. And given that I don't know what this surface looks like, I want to ask the question, can I view x as being a function of the other variables? And if so if this is a function of y and z, and notice only because I know that it's a function of y and z, is it even reasonable for me to ask, what is the partial derivative of it with respect to z? Right? You can't take partial derivatives of things that aren't functions. If you don't know it's a function, then the partial derivative doesn't make any sense. Okay, so this is a two-part question. Step one, let's take these one at a time. Can I view x as a function of y and z? This says whatever variable you want to view as a function, take the partial with respect to that variable. See if you get not 0. You're hoping for not 0. Right? Okay, so here we go. The thing I want to view as a function. Taking the partial with respect to that variable. Algebra, 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 and not 0. Yeah? Everybody good? So therefore, yes, I can view it as a function. Please make sure to write all this stuff down. I'm a big believer that this has to be written down before you get into the plugging and chugging aspect of the doing the calculations. If you write down this before you establish that x is even a function of y and z, you're writing down unjustifiable statements, right? You have not established that what you're writing is not garbage. That's not good, right? Okay, so just again, full disclosure, I just want you to know in advance. This is, being as it is, kind of half of the question. Doing this, right? Taking the appropriate partial derivative, computing it correctly, evaluating it at the given point, identifying that it's not 0, and then spiking the football, confirming that yes, it is a function. If you don't do this first, you're probably going to lose about half the points on the problem. Make sense? Everybody? All right. Again, don't say I didn't warn you. Okay. All right. So we've done that. Now we know x is actually a function. So knowing that it is a function, right, I can reasonably ask what is its partial derivative with respect to one of its two input variables. Its two input variables are y and z. Okay. And we're going to use this formula from the previous page. Right? Don't forget the minus sign. Again, huge, important. Don't forget that minus sign. If you forget that minus sign, it tells me you don't understand what these things mean. Sorry, I'm just saying. Right? And then it's all calculation from there. So this partial derivative here. Plug in the value, do the arithmetic, and there's the answer. Yeah? Yes?
So the equation right after the and, do we need to justify that at all, or can we use it after the...
No, you can just cite that. Yeah, you can just, so he's asking about this formula here. You can just cite that. Totally fine. As long as you cite it correctly. Yeah. Yeah. Okay, now, some students point out, so students that skip this part of the problem, students that have not done this, right, will very often complain and say, well, I did compute the partial with respect to x. See, here it is. It's there, right? Here's the problem. That justification, so having skipped this, right, this justification that x is a function comes after you're already treating it like a function. That's no good. Does everybody see why that's no good? You can't justify, your actions after the actions. That's not how math works. So make sure that you actually do this to justify this. Okay, all right. I'm going to have to move on now to the next thing. A quick reminder, this next bit of material actually goes pretty quickly. This is just really kind of a special case, but some kind of cool things happen when you look at a certain special case. So let's look at what I'm going to call a real valued function. By the way, make sure to understand that terminology. Real valued means that you're looking at a function whose output values are simply single real numbers. So real valued is the output is R1, the target is R1. That's all that means. Okay. All right. So if you're looking at a real valued function of several input variables, here's some formulas from back when we were talking about the chain rule. Remember, we made this observation. Again, I think this is a big interpretation of the chain rule, that the Jacobian matrix, the matrix of partial derivatives, laid out in that certain special way, gives you a relationship between input changes and output changes. Fundamental interpretation of derivative, again, my opinion is it's a relationship between input changes and output changes. And this interpretation applies. Let's think about how broadly this applies when you're thinking about derivatives as slopes. Rise over run, okay, sure, but that's output change over input change. That slope is a relationship between input changes and output changes. Velocities. Output changes, namely distance, as relates to input changes, namely time. Right? Every interpretation of derivative that you can think of could be viewed as a relationship between input changes and output changes. So this interpretation of the chain rule as noting that the Jacobian matrix does that. The Jacobian matrix is the relationship between input changes and output changes. I think is just fundamentally hugely important. If you were to take Math 222, right? That's kind of the honors version of this class. They spend much more time than we do talking about this thing, the Jacobian matrix, as fundamentally being the derivative of a multivariable function. So anyway, that's the cell job. Okay, well, now, don't forget the way this Jacobian matrix is organized. In this case, where there's only one output value, that means our Jacobian matrix is going to have only one row, right? Think about how those partial derivatives go into the Jacobian matrix. One output, one row. And then recognize that, hey, those numbers that make up this Jacobian matrix, those numbers, that's the gradient vector. Go way back to 13.6, I guess it was. This was, a notational convenience that we wrote down. That, convenient way of writing down how to write down differentials. Okay. And remember, in that context, we rewrote these equations, or sort of the precursor to these equations is that we rewrote that special case like this. So notice then dot product with the Jacobian is sort of the real valued version of multiplication by the Jacobian matrix. Okay, so this is just an observation of how our general equation changes in the special case of a real valued function. Okay, so we're going to be looking at these equations here. Now, the nice thing about dot product with the gradient is the gradient I can interpret geometrically. Let's take a moment to recognize we didn't really have that with a Jacobian. A Jacobian's a matrix. We can't draw pictures of matrices. What does a matrix look like? It doesn't really have a geometric interpretation that we can talk about here. Vectors, though, totally. Right? The gradient vector, I can view it as an arrow. It's a direction and a magnitude. So we have a geometric point of view on something that we previously did not have a geometric point of view on. Here's another thing. Dot product. We have a geometric understanding of that. Right? So the fact that we have geometric points of view on some of the objects in these equations is that's a foot in the door to maybe get some sort of geometric interpretation, or at least different interpretations of what is this, when you relate input changes and output changes, what does that look like? Okay. All right. Okay, so let me just complete this picture. Gradient vector, right? Whatever your input change is, that dot product gives you the corresponding output change. Okay. All right. Now, that's all just set up. Now, I'm going to make the following definition kind of like how the book does. I'm going to put an asterisk on this, and I have to come back and talk about in a moment. Reminder, dot product with the gradient relates input changes and output changes. Dot product with the gradient. Okay, so here it is, dot product with the gradient. Here's the special case that I want to consider now. The special case is suppose that the input change is a unit vector. Let's just say, hypothetically, were that input change to be a unit vector, what would come out of that? And it turns out there's some nice answers. It's going to take us a while to work through the algebra, but this is the object that we want to consider. What is the output change when we consider the scenario of a real valued function and an input velocity that is a unit vector? And so anyway, here's the result. So this df dt, the resulting output velocity, we call it a directional derivative. That's the term, directional derivative. Here's the notation for it. It is, the resulting output change, right? And let me just remind you, in this class, the way this book is doing this, don't forget that the word directional derivative does not mean simply what is the output change. Directional derivative means what is the output change when your input velocity is a unit vector. And that is essential to some of the conclusions that we're going to draw about this. Now, let me talk about why they use the term directional derivative to address this question of when the input velocity is a unit vector. If you think about it, let's go way back. Very first day of class, second day because procedure was on the first day, but the very first math day in this class, what is a vector? A vector is a direction and a magnitude, right? Well, direction and a magnitude, if direction is what you're interested in, hypothetically, if you're interested in isolating just the direction, try to find some way of ignoring the magnitude, get rid of the magnitude. In other words, look at the resulting unit vector. So we talked about this before. We interpret unit vectors as interpreting directions. So directional derivative says, okay, derivative, but in the case where we're indicating only the direction, not the magnitude, only the direction means that input vector is a unit vector. That's kind of the idea of the terminology. Now, before I get into any other stuff, let me just acknowledge a really unfortunate terminological awkwardness. Not all math books and mathematicians use this same interpretation of the term directional derivative. Lots of other books and plenty of mathematicians, including this one, prefer, if it were, up to me, which it's not because we're using this textbook, we're going to stick with the conventions of this textbook. I like to point out that this is a really useful construction even when dx is not a unit vector, and this is something that deserves a name, and I know the difference between a unit vector and not a unit vector, and I can just, when this is a unit vector, interpret it appropriately, and when it's not, I can still use this equation, right? So lots of mathematicians and other people who use multivariable calculus that are not necessarily mathematicians use the term directional derivative independent of whether the input vector is a unit vector or not. All right? And so I've had this conversation with more than one mathematician, in fact, and I bring up this question, and they're like, what do you mean the input vector has to be a unit vector? Why? Why would you do that? What's the point? Right? So anyway, there's different points of view on this. And just the main reason I'm making a big deal out of this, it's not because that point of view is going to come up in this course. I'm going to try to stick exclusively to using this term directional derivative as the book uses it, namely the input velocity is a unit vector. But y'all will, of course, have lives outside of this course. Right? And I just want you to know that out in the real world, anytime you hear the term directional derivative, your ears need to perk up and think, uh-oh, what is it? Which camp is this person in? Right? And so what are you talking about? So be sure to look for cues, right? Every time you see the term directional derivative and they tell you, oh yeah, let's compute the following directional derivative, your eye should go straight to, okay, what is this input velocity vector? Look elsewhere in your context, and is this a unit vector? And if it isn't, okay, well then this person's in the other camp, and okay, fine, no problem, and just interpret it appropriately in that context. Okay. All right. Okay, so, and I'm out of time. Okay, so we will pick up here on Monday. Y'all have a great weekend.